Question number 12 says a horizontal 810 Newton merry-go-round of radius 1.7 meters is started from rest by a constant horizontal force of 55 newtons applied tangentially to the merry-go-round. Find the kinetic energy of the merry-go-round after 2 seconds. Assume it is a solid cylinder. So what we have is the weight of the merry-go-round is 810 newtons. Its radius is 1.7 meters, and it's got a force equal to 55 newtons being applied to it. So what we need to do is take the weight and come up with a mass. So we divide 810 by 9.8. And what we're really doing is we're trying to figure out what this number is going to be at this time. So I is equal to, for general purposes, I is equal to the mass times the radius squared. But whenever you have an oddly shaped object, such as a cylinder or a sphere or a disk, you have to look at table 8.1 in the textbook, and you will see that I for this disk is equal to 1/2 of mass times radius squared. And so from that we can take the mass that we get from dividing by 9.8, which that makes the mass is equal to 82.65 kilograms. And we can plug the mass in there, and we already have, or actually not this one right here, we already have the radius, so the radius is 1.7 squared, and then the mass times 82.6. Plug all that in, and you'll find that the moment of inertia is equal to 119.4. Now, in order to figure out the angular speed, we have to find out the angular acceleration that would be caused by 55 newtons on this mass. So in order to do that, we can set up the equation. So we know that torque equals the moment of inertia times the angular acceleration. And we know that torque also equals the force times the radius. So we can substitute in, and we can say that force times the radius equals the moment of inertia times the angular acceleration. And since we just solved the moment of inertia, we can go ahead and plug in 119.4. We know that the radius is 1.7 meters, and we know that the force is 55 newtons. So we can plug all of that in and solve for the angular acceleration. So 55 times 1.7, then divide that by 119.4, and angular acceleration is equal to 0.78308, and we'll stop there. That's going to be our angular acceleration. And with this, we can kind of go back to the kinematic-like equations for angular speed. So the final angular speed equals the initial angular speed plus the angular acceleration times the time. And we know that the initial angular speed was 0, so that can just be ignored, and we can just take our 0.78308 and times it by 2 seconds. So the final angular speed was equal to 1.566 radians per second. And with that, we have enough information now to go back and plug in and get our kinetic energy. Before I plug it in, I just want to point out, if you remember when we were dealing with linear movement, kinetic energy equaled 1/2 of the mass times the velocity squared. And so you can see that there's an analog in this, that the moment of inertia is kind of analogous to mass, and the velocity is kind of analogous to the angular speed. And so anytime in angles, if you would use kinematics, if mass would have been used, then moment of inertia will be used instead. Anytime velocity would have been used, then angular speed will be used instead. Okay, so with that, we can plug in our values. Kinetic energy equals 1/2 times 119.4 times the 1.5 1.66 squared, and then you'll have your kinetic energy. So the kinetic energy will equal 146.41 joules.